Hey everyone, thanks for coming to my talk. So I shortened the title a little bit because it looked like an academic paper title when I put it on a slide, but we're going to be going over the same concepts. So we're going to look at navigating the Apple machine learning landscape. And as you know, my name is Meghan, and I'm a developer at Novoda. It's an app consultancy, and I work in the Berlin office. I work on some iOS projects and some early-stage machine learning projects. OK, so we've all heard the excitement about how Apple continues to provide us with more machine learning offerings. So this is a great opportunity for people to get started with using machine learning in your apps, even if you have no experience at all. But as was mentioned, it's confusing to know where to get started, since there are so many options. And I'm not even showing absolutely every option, and the list keeps growing each year. So how many people have used any of these before? I know some people raise their hands for, OK, so about half. So then this will be a review for some people, and then maybe some of the tools that we'll go through will be new for others. So hopefully everybody can learn something from this. A lot of these are surprisingly simple to use, and it's kind of a la carte, so you can choose whichever difficulty level and whatever purpose suits your needs in your app. So we can't go through all of them because this would take probably like a couple of days, but we are going to go on a road trip through some of these tools. So we're going to check out Vision, CreateML, CoreML, and Turi Create. But before we pack our bags and start on this road trip, we should remind ourselves about why we're going in the first place, because machine learning is pretty cool, and it's everywhere nowadays. Every other tweet I see is about machine learning. But you shouldn't just use it for the sake of it, right? You should have a reason for using it. So why should we use machine learning at all? So it's helpful to remind ourselves of some of the tasks that are relevant for using machine learning and most suitable. So if your app is trying to perform any of these tasks, then it's suitable to try to use machine learning. So first would be detection. So this is very simple detection of rectangles, faces, barcodes, or text. Next would be classification. This is also a very standard example. So image classification, text classification, activity classification, which is pretty cool and not so common yet. Hopefully it becomes more of a use case. But you can take sensor data from the phone and the watch, so accelerometer and gyroscope data, in order to try to classify different activities. Apple does this, as you know. You get you can see which sports you're playing. They even have like yoga support and all these other more custom sports now. But you can extend this to be very custom activities of your choosing. You can also classify any type of column data. We can do style transfer, so you can change your photo to be in a style of Picasso or Van Gogh. You've probably seen this before. But you can extend this with Apple's offerings to be of any artist that you'd like, even if you're an artist yourself. We can do image similarity, object detection, natural language processing, and regression. OK, so let's be more concrete about what we're talking about when we say machine learning in your apps, because there is some confusion sometimes. So there's two main parts of machine learning, and that's training, and that's the inference part. So training still has to be done on the laptop or the server or the cloud for what we're provided from Apple out of the box. Maybe next year we'll get training on the device. We'll see. But once we have the trained model, then we can use that to put it on the phone or the watch or the TV to perform inference, so to do predictions. And as a review, training is a process of creating a model that will be able to perform the tasks that you want to do. And we're going to pass it a ton of data in order to have the model come up with parameters, one of them being weights, to give to each node in order to that will be able to give us a good prediction after we pass it a ton of data. So as we go along, the model is deciding to update its weights accordingly if it predicted something right or wrong. Yeah, like the idea is that this improves over time. You've probably heard this before, so I'm just going to do like a very brief summary. And at the end of it, you should have something that's pretty accurate that you want to be able to use in your apps. OK, so why would you want to take that model and put it on the device in order to do predictions? So there are some advantages of this, and probably people know this already, but I just want to review this. So the first advantage of this is user privacy. So the data that's passed into the model when it's on the device is kept local. So this is advantageous if the user is worried about sending the data off to the server. The second is the low latency user experience. So this is particularly important if you suspect that your users are going to have a poor network connection, or if you're trying to perform many predictions in a short period of time. OK, so now that we understand why we would use machine learning at all, we can start our road trip. OK, so how many of you skipped one? How many of you play board games? OK, oh, a sizable amount. Yeah, I also play board games. I'm a huge fan. Some of my friends that I like to play with, or I've convinced to play with me, though, sometimes they're not so keen to learn all the new rules of a game that has tons of pieces and tons of rules. So, of course, you should read the instructions, but maybe it would be helpful if you have an app that you can take a photo of one of the pieces, and it can tell you the function of the piece and what the piece is called. So a player could have a reminder as they're trying to learn the game. So for our example, we're going to try to classify board game pieces for a game called Agricola. OK, so our machine learning task is the user should be able to take a photo of an Agricola piece, and when the app should be able to classify the board game piece with the correct label. So that's the term for it in machine learning, is the label. So what we would try to do for this is first we would probably try to detect the game box. So this would be rectangle detection, and then the second part would be to classify the Agricola piece within the rectangle, so to do image classification. So we're going to have two different tasks that we're going to try to perform using Apple's offerings. So let's go to our first stop on our tour. So first stop is the vision framework. So what are the capabilities of the vision framework? It's a framework that's built right into it's a framework in itself, so you don't actually need a model. You can just call directly to these APIs in order to do any of these tasks. So this offers you detection of rectangles, faces, barcodes, and text. It also has object tracking and image alignment. So there we go. That's our first part of our machine learning task is done right here. So we can just do rectangle detection just by using the vision framework. But how do we use it? What's involved in this? So there are 4 steps in this. And first, we have to create a handler. Then we have to create a task-specific request. And then we have to send the request to the handler. And then we have to handle the results. So it's really simple. So first, the handler is just going to be a VN image request handler. And you pass in the image and the orientation and any special options that you may have. The orientation is particularly important because if it's expecting it to be in portrait mode and you're sending it in landscape mode, it might have a hard time. And next, we're going to create a request. So for the rectangle detection, we're going to create a VN detect rectangles request. So this is very similar for the other tasks. It's just changed to a face rectangles request or a text rectangles request or anything else similar for whatever the name of your task is. And we're going to pass it a completion handler. So you can pass whatever you'd like to do once you get the results back. OK, next we're going to be performing the request on the handler. So it's really as simple as just calling handler.perform with the request. So it can take an array of requests, but we only have one in our case, so we'll just pass the one. And of course, you want to handle the error. OK, finally, we'd like to handle the results. So the results will come back on the as an optional request with the results object on it. And this will be of type VN rectangle observation. So you want to take that and then do something with these results. It's going to send you back the bounding box coordinates. So in our case, once we have the bounding box coordinates, we're going to want to crop out the rectangle, and then we're going to want to use that cropped image to perform image classification. OK, so now that we have the bounding box coordinates, we have checked off the first part of our approach. So we've detected the rectangle. And next, we have to classify the Agricola piece within the rectangle. So this is your standard image classification problem. Why did we want to restrict the input image to the box? So it's going to be much easier if you are restricting the constraints of what the user is going to be sending in. So this may seem obvious, but it's something that you should try to utilize as much as you can because if you are restricting the user to sending in inputs that are just in that gray box, then the training data you're providing just has to be training data of the pieces in that gray box, not training data of the pieces in like a lot of different environments. So this makes it easier to train an accurate model because the realm of possibilities is a lot smaller, and it's also faster to collect image data because you only need to go through like so many permutations of what the box could be, what it could look like in the box. Okay, so we're going to use CoreML for this because we can use a out-of-the-box CoreML model for standard image classification of everyday objects, so recognizing a laptop or a coffee mug, but we don't have anything out of the box for Agricola pieces. This is something that's custom, and we have to train ourselves. So CoreML was released this year, and we can train a model entirely in Swift in an Xcode playground with so few lines of code. And this is something that was a big breakthrough in order to like democratize using machine learning for training, because previously you had to do a lot more steps and also work outside of the Swift language in order to train your model. So what can we do with CoreML, though? So we can't do everything. We can do image classification, text classification, and classification and regression of column data. So for classification of column data, you can think of an example like there's an open wine data set, which has like wine acidities and alcohol content and color intensities and other characteristics. And you could build a model that tries to classify a wine based off of if you had this data. I can't think of an example of why you want to use this in your app, but this is an example of just like a classification of regular column data. For regression, you can think of a problem, any problem where you're trying to find the relationship between like input factors, features, and an output. So if you're trying to find the relationship between prices of houses in a region based off of the number of bedrooms and proximity to public transit, et cetera, this is a regression problem. So you can do this, which is like interesting to think about because yeah, you could use this in many other ways, and people are usually advertising this. So we need to collect the data now. So how are we going to go about this? So the most important thing is that we're collecting images that are representative of real-world use cases. So we made this very easy for ourselves because we restricted ourselves to this, to the inside of the board game box. But we want to make sure that we are varying the angle and the lighting conditions, because although it may seem trivial for a person to recognize one piece in dim light versus bright light, we're trying to teach a computer how to do this, and it sees it much differently. So how many examples, how many data points do we need? Apple recommends that you can use at least 10 images per label, but I think that ideally you should use much more because it's difficult to imagine that you can represent all of the real-world situations in a way that you'll be able to use this effectively just by having 10 images. So if you can get more, then you really should. You need to make sure that you get an equal number of images for each label. So this is very important because if you get 500 labels for one piece and 500 images for one piece and 15 for the other, it's going to have a really hard time training this model. This is also just another minute detail. Make sure that you try to get images that are at least 299 by 299 pixels. So if you don't want to go through trying to collect maybe 100 images per label, then you can come up with some tricks for collecting this data pretty quickly. So one trick is to take videos of the data, of the conditions instead. So what I did was I just put the box and with a piece inside in various light conditions, and I took a couple of videos on my iPhone. And I also made sure that I was zooming in and out in order to get the piece in various different angles and with various different various different perspectives. So once you have this, you can just run this through a tool called FFmpeg, which will allow you to take the video from your iPhone and then just extract the frames out from that. So You need to make sure that you are taking this at a reasonable sample rate, though, because if you have it at a high sample rate, then the images that you're extracting out are going to be virtually identical. So they're not really like unique images. So I set the sample rate like quite low, so it's just 5 frames per second. So I was able to get 100 images, though, with just 20 seconds of total video, though. So that's pretty quick to collect the data. OK, so now that we have the data, let's prepare for how CreateML expects it. So CreateML just expects you to put the data with the subfolders for each of your labels. So the board game pieces that we're classifying are the border piece, the feeding trough, the reed, the stone, and the wood. And so we have folders for each of these. And then we nest those into a test folder and a training folder. And you have to split this data in a way where you have some of it for training and some of it for testing. And there's no real exact answer for this, but a rule of thumb is to try with 80% training data and 20% testing data. And if this isn't working, then you can try to adjust this. Or you can also try various other techniques for correcting this, so we'll go through. So once we have our images prepared in the training and test folders, we're ready to train the model using CreateML. So this is what it's going to look like when you launch Xcode Playgrounds. So you have 2 ways of training in CreateML. You can do it via Playgrounds with the live view, and it's interactive, or you can write a Swift script. So I chose to do it with the UI because it's nice to see like how simple this is, and you can also see how it's processing your images and how it's labeling them once it's done. And it's nice to see the feedback loop. So all you do is import CreateML UI if you're using the UI one, and then you just create a builder called ML Image Classifier Builder, and then you just call Show in Live View on the builder, and it's going to launch this view in the live view where you see the classifier that you're trying to make. You have to rename it to whatever you want, and then it prompts you to drop the images to begin training. So once you do this, you can just take that folder you had for training data and just come and drop it in there, and it's going to start training. So so basically, it's just going to first process your training images, and then it's going to take a random sample of 5% of the training data and hold it off for validation data. So validation data is going to help your it's going to help the training process to figure out if it's overfitting to your specific training data, and it's a mechanism in order to make sure that this is not happening, and it will be very obvious when this is happening because your validation accuracy will be very different from your training accuracy. So once you do this, it's going to train the model, and it takes really just a couple of minutes. OK, so once it's done, this had 100% training accuracy and 100% validation accuracy, which is kind of suspicious, actually. But we have to remember that these were very constrained conditions. We were expecting the data to be in this world that we created, which is just in the box of the game. And so it would be more likely of a scenario for you to get 100% when you have such constrained conditions. If you're trying to classify like cats and dogs in the wild, and you're training with images for that, this would be very suspicious, and you should look into it why it would give you that. So once we are done with this, we can see we can also see the iterations over time while it was training and the debug output, and we can see how the training accuracy was over the iterations as well as the validation accuracy. So as you can see, for the first iteration of passing data through, we had 77% training accuracy and 77% validation accuracy. So we would expect this to increase over time, and we should expect the training accuracy and the validation accuracy to parallel each other mostly, because that means that you're not overfitting to your training data. So we reached 100%, so at the 10th iteration, so there's really nowhere to go from there. But let's say that we were only at 60% training accuracy and around the same validation accuracy at the end of those iterations, then that would be a clue that we aren't running for enough iterations. because it still has more to train in order to reach a higher level of accuracy. So you should, in that case, just increase the number of iterations, which you can do if you drop down the arrow in the live view. So, okay, what is happening behind the scenes? Because while this is really simple and a really good place to get started, we should know a little bit about what's going on, just so that you can know the intuition for how this is working. So why were we able to classify, make an image classifier with so little data and in such a fast time? Because probably a lot of people have heard that you need tons of data and you need a lot of time and a lot of compute power in order to do this, or at least that was the case fairly recently, a couple of years ago. So the idea behind this is transfer learning. And if you look at training a network, say you're trying to recognize cars. This is a really nice visualization I found online. I don't have it for our exact Agricola example. But if you're trying to classify cars and you're using a convolutional neural network for this, then your input would be an image of a car, and it goes in as the pixel values in the matrix. And then when you're doing training, traditionally you'd be training the entire network. So you need to you need to be able to pass enough data and send enough iterations in the training process in order to update the weights for every single one of those layers. Because your input is going through transformations as you're going through each of these layers. So this takes quite a lot of time and quite a lot of data and quite a lot of compute power to do well. But if you see what's happening at each of these layers, so on the top of the nodes of the network, you can see what the network is seeing at those layers. You can see that in the beginning, it's picking up on very basic features of the car. It's picking up on lines, and you can see some circles. And so very basic features that are found in a lot of different objects that you see in the world. And then when you get towards the middle, then it's starting to pick up on more like higher level features of cars. So you can see a door, you can see a wheel. I think I can see some of the windows. And then when you get towards the end, that's when it's being able to recognize the entire concept of a car. And so if you think about how it's composing the different parts over the different layers, then you can maybe think, okay, many of these layers should be reusable towards a lot of different objects that you're recognizing, not just cars. And so that's the whole intuition behind transfer learning, is that instead of training a network from scratch, you can actually reuse almost all of the layers from a previously trained model for a model that's trained to recognize most objects in the wild, like 1,000 different categories. This is the standard example. And we can just, for our training process, just train the last layer of the network. And so since you're just doing the last layer, it doesn't take much compute power or data or time to do this. And it's fairly agreed upon that this is a good approach for most image classification, unless you have like a task that's super unique. If you're, for example, trying to recognize cardiograms, then maybe this isn't something that you should go with. But if you're trying to recognize Agricola pieces, then they have a lot of similarities to a lot of other objects. OK, so we had trained our model, and now we know the intuition behind it. But we should evaluate it on the test data, because we, at this point, only know how it did on the training data and that small bit of validation data. So we need to, this is important because we care about what the model is going to do, and it's trying to generalize to new data. And so in order to do this, we just drop the test folder into the live view. So where you see one of the border pieces, this is just where I dropped the test folder, similar to where I dropped the training folder before. And it will go through and evaluate our model on the test images. And I've said this before, but I'll repeat it because it's super important. You need to make sure that your test images are totally distinct from your training images. Otherwise, it's not going to be accurate because you will just be evaluating on images that you were training with before. So once you have done this, it will take a little bit longer to go through this. I think it took 10 minutes for me, but it will give you an evaluation accuracy. So it's 96% for this, so this is something that's definitely acceptable. And it will also print out some statistics. So in the debug output, you can see that we have the precision and recall. So you can see for each class or label, we have a precision percentage and a recall percentage. So precision is the false positives that we got. So so it's saying that 97% of the time for wood, we didn't get false positives. And for recall, it's telling you about the false negatives. So for wood, we 83% of the time didn't get false negatives. So this can tell you whether or not two categories are really similar in their training data, and you can try to bulk up the training data in those categories if it's at a level where it's problematic. So we are done evaluating this, and we've accepted it, so we want to save it down so that we can use it in our app. So all you do is click Save, and then once you do that, it's already in the CoreML format that we're expecting. So this is ML model format. And something to note that is unbelievable is that this is only 66 kilobytes. So this is a huge improvement, because some of the models, for example, for recognizing 1,000 everyday objects, were around 50 megabytes, and then the one for optimized for mobile was I think around 5 megabytes before. So going down to on the order of kilobytes is a huge improvement, because it was holding back people using models to do inference on device if you have quite large models to have in your app. So, OK, we have this in the CoreML format, and now we want to be able to actually put it in our apps. So now we need to visit the CoreML stop of our tour. So what are CoreML's capabilities? So the first and foremost one where you are going to be using the most would be to perform predictions using the model. And some features that were added at WWDC this year were quantizing the weights of your models. So in addition to having models that are a lot smaller right off the bat from CreateML, if you have models from somewhere else which maybe don't have the same optimizations as CreateML has, then they still could be quite large. And so one of the ways you can reduce the size of this is, by default, the weights in the model are 32 bits, and you can reduce this to 16 bits per weight or 8 bits per weight, all the way down, I believe, to just 1 bit per weight. Of course, this is going to come at a trade-off of how good the model is at still performing predictions. So you need to make sure, if you quantize your weights, that you also test to make sure that it's still within the same range as before. You can also use CoreML to perform batch predictions. So if you want to send a lot of predictions at once, and it will do a lot of performance improvements for you. The last capability that they added this year was creating a custom model layer. So this is really out of the scope of this presentation, but I still wanted to mention that's available, because you are able to support any type of layer for any type of custom architecture that you want to use. OK, so if you're using CoreML with an image classifier, you can use CoreML the standard way, where you're running predictions on it directly, or you can use it with vision. And that's what Apple recommends us to do, because they will do some pre-processing for us. So if you're using CoreML for image classification, you have to work with CV pixel buffers, and this is not ideal. So if you're using vision with CoreML, then you can instead work with CG images. So this is a lot easier to work with. So for this, it's very similar to our vision request from before. We just have an extra layer, or sorry, an extra step at the beginning. So we need to first create the vision CoreML model. And after that, we just create the handler, create the task-specific request, send the request to the handler, and handle the results. So for our Agricola piece classifier, we just take that model and we just drop it into Xcode, and it's going to take the ML model format and auto-generate the Swift file for us, so we can directly instantiate it. So we have the model, and then we want to wrap it in a Vision CoreML model object so that we can take advantage of working with CG images. So we'll first do that, and it can return a nil. So we need to make sure that we don't have that. So then after that, we create the handler just like before, and we are just passing in the CG image and the orientation. And then we create a request, this time with a VN CoreML request. And we just simply pass in the model and the completion handler for this. We call perform on the handler with the request. And finally, we handle the results. So this is going to come back just as before as an optional request with results on it, and that has optional VN classification observations. And we want to be able to do something with the results. So for this app, I didn't go through the whole process of making the app in the UI, but you would probably want to do something like say the name of the piece and what the function of it is, and any other details that would be helpful. OK, so problem solved. We detected the game box using rectangle detection, and we classified the Agricola piece within that rectangle. So the next challenge that I want to do is something that people have probably seen for like having your images look like Picasso or Van Gogh, but I wanted to transform images into curated styles that I picked from some artwork that I found on the internet that I really liked. So I wanted to transform a photo of Stockholm into the style of this piece of artwork that I found online. So in order to do this, you can't use CoreML, because CoreML's capabilities didn't provide what we call style transfer, which is what this task is. So in order to so for using this, we use Turi Create, which is the robust Python training framework. So unfortunately, this isn't in Swift. I'm thinking that perhaps a lot of the Turi Create and CoreML tasks are redundant, and I think that they might be like shifting the Turi Create capabilities into CoreML over time. So we'll see. Maybe we'll have this in the future. But for now, we have to use it in Python. So the additional capabilities of Turi Create, besides what's already available in CoreML, are style transfer, activity classification using the sensor data, and then image similarity, recommendations, and object detection. OK, so you can just use your Python installation on your computer, but it's probably easier if you use something like virtualenv. So that's what I use, or you can use Anaconda, or you can even use a Docker container. So to set up Python using virtualenv, you just call virtualenv with whatever you want to call it, and then you just activate that virtual environment. And then after that, you have to install the requirements that we need in order to run Turi Create. So you, in theory, should only really need pip install Turi Create with this is the beta version that's out right now, but there's some dependency that it needs where it needs the requests at a specific version right now. So you also need to install the requests for version 2.18.4. And then I choose to run my Python scripts in Jupyter notebooks, which are similar to Swift playgrounds. So they're really nice to work with. They run in the browser, and you can have inline markdown in order to comment what you're doing for a specific part of the script. And you can run through it like line by line, too. So so I'll show you what this looks like. So once you have the dependencies installed, then you can just run Jupyter Notebook in your terminal, and then it launches the browser. So I already have this up because this particular task of style transfer does take quite a while if you're running it on your laptop, because right now it only supports the CPU. They're supposed to be able to support GPU for style transfer very soon. I saw in the issues, but not at the moment. So it took 3 hours to train this. So I'm not going to go through this in the presentation. But this is what it would look like. So it's just actually maybe a dozen lines of code. So first, you just have to import the dependency. And then in order to be able to train this network, you need 2 different like folders of data. So you need a style image set, and you need a content image set. No. Let's see. Thanks. Is it just? Let's see. Do you think that you could maybe help with this? Sorry, 1 second. I think it just went to one of the I'm not sure which desktop it's presenting. Oh, it's mirroring. 1 minute. Okay, perfect, great. I don't have too many slides left, so this should be easy to go. Okay, cool. So, right, you didn't miss much. Thank you. Okay, once you have this open in the browser, then you can see the first step would be to load the style and content images. So what are these? So the style images will just be a set of images of artwork that you want to be able to do style transfer with. So I just chose like a couple of different artwork on the internet that was available for reuse that I found nice that I wanted to use to style my images with. And so you can actually just have one style if you just want to do that. So it's not a training task which needs a lot of data. The next is the content, and this is supposed to be like representative of the content that you're going to be performing style transfer on. So if you think that you're going to be taking selfies and then you're going to be doing style transfer on it, you should probably have images of faces. If you're doing it for like cityscapes, then you should probably include a content data set of a bunch of cityscapes. So just so that it has an idea of what it's going to be doing the style transfer on. So since I knew I wanted to do this for Stockholm, I just included a bunch of like street level images of Stockholm and Berlin, where I live, and just a couple of other cities that I had in my photos. So next we train the model, and this is just simply we call style transfer on Turi Create, and the create method, which takes in the style and the content and the max iterations. So the max iterations, I believe the default is 5,000. This is going to give you a really, really good style transfer, but it's also going to take days and days with the current setup that they have for running on the CPU. So yeah, supposedly that's supposed to be fixed kind of soon, but you can get a good basic transfer with 300 iterations, and on my laptop this took 3 hours. So you can just run it, and then yeah, it will be done like within the morning if you were to run it. So it's a little bit like different how this works as far as the accuracy, because there isn't really any accuracy for style transfer, right? Because there's no like objective measure of whether or not it's accurate, because that's not the nature of it. But you can see the elapsed time and you can see the loss. So the loss of it is decreasing over time, and you can see that there's still quite a bit to go, but we are only doing 300 iterations. I imagine if we did 5,000, it would probably be a lot lower. So once you have that, then you can load your test images in order to like see how well the style transfer is doing. So I made a test data set just with a couple of Stockholm photos in it, and then we can see how this looks using Turi Create's interactive explorer. So basically, we call model.stylize on the test images, and then we choose which style we want to apply. So I just chose the style 1 because I liked all of the ones that I gathered. And then we can explore these, and what comes up is, so this is just like one of the photos of Stockholm with that particular style applied to it. So it looks like it's pretty good, even though it was just for 300 iterations. And if we're OK with this, then we can export the model. And it's just this one line, model.export CoreML, and then you give it a name, and then it's ready to go in ML model format. So you can use this with CoreML to use directly in your apps. So OK, we are done with Turi Create now, and just have that's the end of our road trip. And so I hope that you enjoyed going through the Vision framework and CreateML and CoreML and Turi Create. And I hope that you feel empowered to start using machine learning with your apps, because it's super simple. And if you want to do something more advanced, you can, of course, go go further into Turi Create, and you can also use any of these third-party frameworks and convert them back to CoreML format. So we didn't have enough time to go through all of this, but you can use TensorFlow, you can use Keras and scikit-learn, and any of these that are compatible with converting to CoreML format. So it's kind of the sky is the limit if you want to keep going with this. And that's all.